Me. So I'm going to tell you about this joint work with Daniel Greer, Alex Kersner, and Luke Schaefer, all of whom are at IQC and are amazing collaborators. And we have a paper that was recently uploaded, which contains the results that I'll tell you about today. Okay, so this is kind of like the overall structure. We're going to do some introduction and motivation, and then I'll tell you about our results, and then I'll go into the techniques. And I'm okay with not getting through everything, or like I would rather that you understand things and that we have a discussion than that I get through all the slides. So feel free to interrupt if you have questions. Okay, so this is kind of like some very broad motivation, like why, I mean, the sort of general topic of the talk is about classical simulation of quantum computers. And so why should we care about classical simulation of quantum computers? Well, we believe that quantum computers can't be efficiently simulated by classical computers. We believe there are exponential quantum speedups. So then why should we improve classical simulation algorithms? Well, it's interesting to understand what exactly is the thing that's hard to simulate about quantum computing. So quantify those resources that are actually hard to simulate. Of course, classical simulation algorithms can be like practically useful if you have a small quantum computer and you want to, verify that it's working correctly. But of course, at some point, that's going to probably not, at some point, you're going to build larger and larger quantum computers, and eventually you'll have to build confidence without that ability to classically simulate. And finally, we should also work on classical simulation algorithms to give confidence that this belief that I wrote above is true, because if we don't work on it and we don't try to understand it and prod this in new directions, then we better be pretty sure that it's true. And finally, one thing that's not written here, sort of delineating the boundary between classically simulable and quantum advantage, also helps us identify places where we can get quantum speedups that are just beyond what can be classically simulated. And that's sort of relevant today as these small quantum computers are being built. Okay, that's kind of like a big picture setup. And if you ask me, well, how do you simulate a quantum circuit on a classical computer? I mean, the bottom line is that, in the general case, there's really not that much you can do, and the algorithms that have been presented have exponential scaling in the number of qubits or the number of gates, and we believe that that's best possible in the general case. So the most naive algorithm you can think of to simulate a quantum circuit, you take the quantum state of n qubits and you represent it as a complex vector with 2 to the n entries. And then every time you apply a 1 or 2 qubit gate, you multiply this vector by a sparse matrix. And so if you have m gates and n qubits, this very naive algorithm has exponential runtime and exponential memory requirements. So that's, kind of just the most naive thing you can do. There's another algorithm where you perform the matrix multiplication as a big sum, and each term in the sum has low memory requirements, but still you need to have a runtime that scales exponentially with the number of gates. And, of course, the number of gates should be at least as large as the number of qubits, right? Because otherwise you can just remove certain qubits that are not being acted upon. So the point of these slides is just to, remind you that we don't have good simulation algorithms that are better than exponential scaling in the number of qubits in the general case, and we don't think they exist. Okay. On the other hand, if the circuit has a kind of geometry that is nice, then you can exploit that. So moving now, beyond the general case and now restricting ourselves to circuits with what I'll call a nice geometry, and we'll talk about what I mean by that. If you have nice geometry, then you can exploit that. And let me just describe how that goes. So let's consider, here's a quantum circuit that's very simple. And, more generally, we're going to consider constructing a graph from a quantum circuit in the following way. So we're going to add a vertex at every gate and every wire of the circuit. So those are the black dots that I've superimposed on the circuit here. There's one for every gate and one for every wire. And then we're going to connect them up whenever a gate is connected to a wire. So, you know, if I now remove the underlaid circuit, this is the graph, okay? And a sort of very seminal result from Markov and Shi from 2005 tells you that the quantum circuit can be simulated with a runtime that, you know, is not exponential in the number of qubits, but instead is exponential in the tree width of this graph. So I have not told you what tree width is, and I won't tell you until later in the talk, but for now you can just think of it as roughly a measure of how tree-like the graph is. So remember that a tree is a graph without cycles, without loops. So this algorithm exploits the circuit geometry, and if the circuit geometry is sufficiently nice, the scaling of this algorithm can be better than exponential in the number of qubits, okay? So let me give a couple of examples of that. Oh, before I do that, let me just mention the simulation idea. How does this algorithm actually work, just in one sort of sentence? So the idea is that you view the circuit as a tensor network to be contracted. And when you have a tensor network and you want to contract it, you can choose the ordering to contract the edges of the tensor network in order to minimize the memory and runtime. And you want to sort of choose it in a lazy way so that, you know, the memory and runtime are minimized. That's all I'm going to say about this algorithm, but I want to just give a couple of examples which show you sort of how it can improve upon exponential scaling in the number of qubits if the geometry is nice. Okay, so here's the theorem again. Here's an example. So suppose we have a circuit where I have n qubits and the qubits are laid out in one dimension. And now at every time step, I'm going to allow myself to apply nearest neighbor gates, like a layer of nearest neighbor gates. So maybe in the first time step, I apply gates on qubits 1 and 2, 3 and 4, 4 and 5, and so on. And then in the second time step, I do 2 and 3, 4 and 5, etc. So this is a one-dimensional circuit because all of the gates are geometrically local in one dimension, and let's say the depth is d. So if I apply this Markov and Shi, result, I would map this to a graph, and the graph that you'll get has n vertices corresponding to the qubits in the vertical dimension, and then the other dimension is a sort of time dimension, and you get a number of vertices proportional to the depth. So this is like a sort of, if the depth is constant, then this is sort of quasi one-dimensional grid graph. And the tree width, what's the tree width of this grid graph? Like the tree width of this graph is upper bounded by a constant times d, okay? So if d is itself constant, like let's just imagine we're talking about constant depth one-dimensional circuit, then the simulation runtime in that case for if d is constant will actually be polynomial. Okay, so this is an example where you can see that instead of having exponential scaling in the number of qubits, now we only have an exponential scaling in the depth, and if the depth is constant, this is a polynomial time algorithm. And you probably, you may already know that 1D constant depth circuits can be simulated in polynomial time using matrix product states, and that's essentially what's going on here. Okay.
Again, how you define the graph from the circuit?
Oh, the question is, how do you define the graph from the circuit? Yeah. Okay, so you place a vertex on every wire segment and every gate, and then you connect them up like whenever a gate touches a wire segment.
So David, if I understand correctly, once you found the way to simulate any particular class of circuit in polynomial time, at this moment it became fundamentally uninteresting.
So I disagree with that statement. I hope that in this talk I will convince you that that is not true. Okay. So maybe ask me again in 15 minutes if you're still wondering that.
So unfortunately, I have to apologize. I must drop off for a critical meeting. So. Oh,
no problem. Well, maybe I can just say. Yeah. So I think personally, I don't think that's true because, of course, there are polynomial quantum speedups, and that's what this talk is kind of investigating to some extent.
But here it would be an exponential speedup, right?
Yeah, so we, the most dramatic speedups available with quantum computers should be exponential, and a lot of the conjectured speedups that we have, like factoring, are of that, believed to be of that type. But there are also possibilities for polynomial speedups, and like that's one of the things that I'm going to be talking about in this talk. So they're not uninteresting, they're just less dramatic. Okay, so this is the 1D circuit, and you can ask what happens if you go to like a 2-dimensional circuit, which is harder to draw because if I have like my qubits arranged in a 2-dimensional grid, and now I'm applying nearest neighbor gates at every time step, and I have like a depth D circuit, then I have to draw something in 3 dimensions, which I can't really do. So I didn't draw it here. But if you map it to a graph in the same way, then you get a 3-dimensional or quasi 2-dimensional grid graph where the 2 of the dimensions are just this grid that we started with, where the 2D circuit is laid out, and the other dimension is like the time dimension and has a width that's proportional to the depth. So what is the tree width of this graph? Well, it's upper bounded by d square root n, in fact. And so this, for a 2-dimensional circuit, you get a runtime which is, ignoring the polynomial prefactor, exponential only in, square root n if the depth is constant. So this, this is a powerful thing, right? Because I said before that in the general case, we don't know any simulation algorithms that do better than exponential in n. But this is exponential in square root n if you have a 2D geometry and constant depth. And this is not just powerful in theory, but also in practice. Since Markov and Xi's groundbreaking result, there have been many sort of practical improvements and sort of implementations of these ideas, of quantum simulation by tensor network contraction and exploiting this kind of contraction ordering. And so here's a table from a paper of Chen et al. From 2018, which shows some of the, probably by now there are even more, but this shows some of the simulations of 2-dimensional universal circuits that have been done in practice. You can see that, the one at the bottom, for example, has 81 qubits and a depth of 40, which is quite amazing.
Can I ask a question? What distinguishes the n directions from the d direction? Why isn't everything symmetric? The way you defined the graph, it was completely symmetric between the two.
Well, I've just, the d dimension is the time dimension in the circuit. So that depends on the depth of the circuit. And of course, you can make a choice as to what depth circuit you might care about. And in this talk, for the most part, I'm going to be interested in constant depth circuits for reasons that I'll explain later. So you can think about that dimension as being constant, like 5 or 10.
Is n the number of qubits or the length of is the length square root n or n?
Yeah, sorry. Thank you for that correction. This plot is not, this figure is not correct. It should be square root n on each side. Thank you. Yeah, that's an important point. Yeah. Okay, so just to recap what we've talked about so far, we were talking about universal quantum circuits, and we said that to simulate a general one requires resources exponential in the number of qubits, but that runtime can be improved if the circuit has nice geometry. And that's kind of, the thing I wanted to say in this first part. And in this talk, what are we going to be talking about? We're going to be talking about exploiting circuit geometry in a slightly different setting where we're interested in a subset of quantum circuits that are not universal called Clifford circuits. So now I have to tell you what Clifford circuits are. And maybe you've seen this before, probably you have, but I'm just going to go over it. So a Clifford circuit is a special kind of quantum circuit where all the gates...
Just before you continue,
yes.
Can I understand this result by Markov and Xi by somehow thinking about the light cone coming from every qubit?
Well, I think not really. I mean, so certainly for constant depth circuits, you have a small light cone, but the result is more general. And I think the right way to think about it really is to think about tensor networks and the memory requirements when you contract them. Like when you have a tensor network, you want to keep track of a bunch of tensors, and then you want to like contract an edge, and now you have new tensors that are defined by the contraction. And the amount of memory that you need in the runtime is determined by like the rank of these tensors as you move through this algorithm. So I think, you can think of it as like when the graph has low tree width, you can make that rank remain small throughout the course of the algorithm.
maybe it's not as optimal as tree width, but maybe one way to see it is you can imagine some sort of a bubble that swallows this structure, and you look at the number of edges that cut the bubble at the maximum point, and that would be the exponent of that. So
Right.
the example that you gave, it's exactly that. It's d times the d times n or something like that, square root of n.
Yeah, thanks, Itai. Yeah, so we're going to just try to apply this idea to Clifford circuits, okay? So a Clifford circuit is a special non-universal family of quantum circuits where the gates, you know, it can be generated by the following gates. We have a single qubit Hadamard, single qubit phase gate, and 2-qubit controlled Z gate. And, you know, the famous Gauss-Meinkel theorem says that quantum circuits composed only of such gates can be efficiently simulated. So this is, you know, in polynomial time on a classical computer. Okay, so this is like a very, very different ballgame, right, from what we were talking about before. Before we were talking about universal circuits where the best simulation algorithm is exponential in the number of qubits. But now I'm telling you that we're going to focus on these Clifford circuits where the simulation algorithm is polynomial in the number of qubits. So let me tell you a little bit more about that polynomial scaling. The quantum state, first of all, like, you know, the statement here is just saying that you can store a state prepared by a Clifford circuit on a classical computer using only n² bits. Okay, so, you know, whereas a quantum state prepared by a universal circuit requires exponential memory just to store, here, you know, you can store a stabilizer state, which is the state prepared by a Clifford circuit using only n² bits. So that's good. And then if you want to update that state when you apply a Clifford in the course of a quantum circuit, you know, if the Clifford gate is just a 1 or 2 qubit gate, then this takes a linear time, you know, and if you want to measure a qubit, then you can do this in quadratic time, n² time. And this was an improvement from the original Gauss-Meinkel theorem due to Gaussman and Aronson from 2004.
Is a measurement in an arbitrary basis or?
Oh, no, here in the computational basis. Yeah. But equivalently, you can measure in the X or Y Pauli bases.
Okay, thank you.
Okay, but if you want to, let's say you want to measure k qubits, well then of course you can just like sequentially apply the single qubit measurement algorithm, and so the scaling there would be k times n². Now I just want to, here I'm going to make a point that maybe people have not thought about before that's kind of new to our paper. So think about the case where k is n, where you want to measure all the qubits, okay? So the previous algorithm, which is Gosset and Aronson, would tell you that this is an n³ time operation on a classical computer. But it turns out that you can improve that using fast matrix multiplication. And this is a small, you know, a contribution of our paper. So in fact, if you want to measure like k qubits, you can do this in time k to the omega minus 2 n², where omega is the matrix multiplication exponent. So this is a number between 2 and 2.3729, which characterizes the time complexity of multiplying n by n matrices. So for example, like if k is n, if you want to measure all the qubits, then what this says is that you can do that in time n to the omega rather than n³. So that's a first small, you know, a first improvement from our paper that doesn't appear to have been observed before.
But this is only for very large n's, right? I mean, this kind of...
Yeah, that's right. So this is not a practical improvement. Our work actually does have a practical improvement for simulation algorithms, but this is not it. This is a theoretical improvement. And the other improvement will be a square root that you'll see later that is in fact practical. Yeah, so this is only observed at large n. Okay, and the second thing that we do in our paper just on these basic Clifford simulation runtimes is that if you wanted to apply like controlled Z gates, these 2-qubit gates on any subset of the qubits, like any subset of pairs of qubits, then you can also do that in time n to the omega, okay, rather than n³. So you know, these are the polynomial cost of simulating Clifford circuits, which are state of the art. So if you apply that to like a Clifford circuit with n qubits and depth d, and then you measure all the qubits, the simulation cost is, well, you have like, in this circuit, you have n times d gates. Each one costs order n to apply, say. So we have, and then when you measure, it's n to the omega. So the total simulation cost, according to the thing I just told you, is n² d plus n to the omega on a classical computer. But I just want to point something out to you, which is that if you run this thing on a quantum computer, the number of gates is n times d. So like, let's say that d is constant. So then we're, the classical simulation is n to the omega and the quantum runtime is n. And omega is at least 2. So is this a quantum speedup? Okay, that's the question that I have for you. And or can the classical simulation be improved? And now, in the next couple of minutes, I just want to tell you about some evidence that Clifford circuits can be more powerful than classical circuits, and so why, give some further, motivation for this question.
David, is the red result total simulation time, is it a theoretical lower bound or is it his best known now?
There's no lower bound. This is an upper bound. Yeah. Yeah. So that's why I ask, can the classical simulation be improved? Yeah. Okay. So I wanted to just tell you that Clifford circuits can, in fact, provably beat classical computers in a certain sense that is not the sense that I was just talking about. Okay. But I want to tell you about this anyway. So this is this story that started with a paper that I wrote with Sergey Bravi and Robert Koenig in 2018, where we show that a constant depth quantum circuit can solve a linear algebra problem that can't be solved by any constant depth classical circuit. So the constant depth quantum circuit, it takes the input to this linear algebra problem A, it applies this Clifford circuit, it applies a constant depth quantum circuit, which I'll talk about in a second. And then it outputs a binary string Z, which solves the problem with certainty. So the circuit is Clifford for any fixed input. Okay, so it's like a controlled Clifford circuit. So this is, if you fix the input, it's a Clifford circuit. Not only that, but it's a two-dimensional Clifford circuit. So you can arrange all the qubits in 2 dimensions and all the gates will be nearest neighbor in that geometry. Okay, and what do I mean when I say it can't be solved by constant depth classical circuits? Well, if you had a classical circuit with the same input, let's allow it to access random bits. And let's say that the circuit is required to solve the problem with some high probability, say greater than 7/8, then we prove unconditionally that the circuit must have a depth increasing with n. Okay, so this is just unconditionally showing that constant depth quantum circuits, even Clifford circuits in a 2D geometry, can do things in a lower depth than their classical counterparts. And let me just say that in our original paper, we restricted the gates in the classical circuit to have a bounded number of inputs, because that seemed like a fair comparison with the quantum gates, which also have a bounded number of inputs. But this requirement was actually removed by Bene, Watts, Kothari, Schaefer, and Tal, who showed that you can do it even, the classical circuit still can't solve the problem, even with unbounded number of inputs gates. And then there were a couple, sorry, go on. Yes.
What is again the properties of the input A in the quantum case?
Oh, the input A just describes the instance of the problem. So there's some problem that I haven't told you what it is, and A just tells you the instance of the problem that you're trying to solve.
But in terms of the quantum state that you input, I mean, in the
it's just a computational basis state.
I see.
Describing the input, yes. Okay. So then we later showed that this this separation can also be shown to be true even if the quantum circuit is subject to noise in each of its components. And then Greer and Schaefer showed that if you extend the task so that it's not just like one problem, but instead is an interactive task with 2 rounds of questioning, then the problem can be even harder for classical computers, even though it can be solved by constant depth quantum circuits. Okay, so what's the point of all of this? The point is just to tell you that even if you restrict to constant depth Clifford circuits in a nice geometry, in a 2-dimensional geometry, they can solve a problem that, in terms of depth, faster than classical circuits. So this is a separation in depth, circuit depth. And the question that I have is there also an advantage in terms of total runtime or the number of operations or gates? So going back to our slide from before and now restricting our attention to constant depth, we have a simulation cost n to the omega for the classical simulation. Quantum runtime is linear in n. And we want to know, can this classical simulation be improved? And we're going to, in this talk, be interested in improving it for a circuit with nice geometry. So like, for example, the 2D circuits we were just talking about. So that's the setup. Are there any questions about that? Okay. So let me tell you our results. So we're going to consider Clifford circuits where all the 2 qubit gates act on the edges of a planar graph. So the qubits are arranged at the vertices of a planar graph. So like maybe this graph. Remember that a planar graph is one where there's no crossings when you draw it in the plane. There's a drawing with no crossing.
Maybe I have a question actually,
Yeah.
just a statement. So is there an instance where you have a lower bound that you can show that it's larger than n?
Sorry, like for the simulation cost on the classical computer. So it has to be at least n, because just to read in the circuit takes linear.
Yeah.
But in terms of like the real question is whether or not there's like here, even if omega is 2, right? If this omega is 2, this is a quadratic separation.
Oh yeah, right. It's bigger than 2. Okay.
Yeah.
Right. Mm-hmm.
Okay. So a planar Clifford circuit, we're going to consider, you know, arranging the qubits in this on a planar graph, and then we consider circuits where all the gates act, you know, either the 1 qubit gates or they act on the edges of the graph. Okay, so like here's an example. We apply some Clifford gates on the qubits, and then apply some controlled Z gates on the edges of this graph, and then some more, and then we measure. Okay. So for example, like the 2-dimensional geometry I was just talking about is an example of a planar Clifford circuit. Okay, and we, you know, at the end we're going to measure everybody, and so we get some output distribution, which is the probability distribution at the output of this circuit over n-bit string. And so like we proved the following theorem, like if you have a depth D Clifford circuit where all the 2 qubit gates act on the edges of a planar graph, so in other words, a planar Clifford circuit of the type I just described, then we give a classical algorithm which samples from this output distribution with a runtime up to log factors n to the omega over 2 d to the omega. So if the depth is constant, this is n to the omega over 2, which is quadratically better than the previous thing I showed you, which was n to the omega. This is a square root theta.
So how are these 2 results live together? So because I thought together before that you said n has to be omega has to be larger than 2.
Omega is between, yeah, omega does have to be larger than 2. So like in this case, if omega is 2 and the depth is constant, then this is a linear time algorithm up to log factor.
But sorry, yeah, but somehow is there no contradiction between these 2 results?
Like this result is an upper bound, right? So this is saying there's a classical simulation time with n to the omega, but this is an improvement on that when the graph is planar.
So let me ask again. So is there a case where you actually can show for certainty that you know, there's some problems for which, you know, or some circuits for which omega would have to be, you know, you get lower bounds such that
no, so let me comment on that. So just generally speaking in computer science, I mean, I'm not an expert in this, but my understanding is that there are no problems where you can prove quadratic lower bounds on classical complexity of solving a problem. There's just not any problems of that nature. So certainly not in this case.
Okay. Mm-hmm.
Okay. So this gives a quadratic speedup for the case of planar Clifford circuits of constant depth. And, you know, the algorithm on the previous slide was n to the omega, but that already incorporates our improvement using matrix multiplication. So the best previous algorithm was actually n cubed. So this is, you know, better than quadratic speedup asymptotic. And, you know, this almost rules out quantum speedup in terms of gate count for these Clifford circuits on planar graphs. Because if you have, like, let's say that omega was 2, then this would really rule out a quantum speedup, a polynomial quantum speedup in that case for planar graphs. Okay, where does this come from? Well, actually, this is not really our main result, or at least it's not the nicest way of stating our main result. It's sort of the easiest to understand consequence, but to prove the theorem, we really prove something about simulation of a special kind of Clifford circuit that prepares something called a quantum graph state. And let me just mention that. Okay, so if you give me an n vertex graph G, then I can define a quantum state of n qubits called the graph state corresponding to G, which has the following form. So I start with all zeros, and then I apply Hadamard's to every qubit, and then I apply a controlled Z gate on every edge of the graph. And these controlled Z gates commute with one another, so it doesn't matter what order I apply them in. So that's the graph state. For any graph, I can define the state. And I'm going to consider a simulation task where, in addition to the graph, I'm also given a Pauli basis, like X, Y, or Z, for each of the n qubits. And the task that I want to consider is measure all qubits of this graph state in the chosen basis. So maybe for the first qubit, I want to measure it in the X basis. The second qubit, I want to measure it in the Y basis, and so on. And so then I have this output distribution P of Z, which is like prepare the graph state, apply a bunch of single qubit Cliffords that rotate to these new bases, and then measure in the computational basis. And this is, of course, a special case of Clifford circuit simulation, okay? So this is, I'm just going to write down what I mean. Like, this is just a formal statement of the task. So we call this the graph state simulation problem. You're given a graph, given a single qubit Pauli basis for every vertex, and you want to sample a binary string from this output distribution. And it's worth pointing out that this graph state simulation on a two-dimensional grid graph is in fact the problem that achieves a quantum advantage in terms of circuit depth from our paper from 2018. So this is like highly relevant to the things that are motivating our work. And even though this, as I mentioned, is a special case of Clifford circuit simulation, in fact, it encompasses Clifford circuit simulation in the following sense: that if you care about general Clifford circuit simulation, you can take a Clifford circuit and map it to an instance of graph state simulation using like known techniques for measurement-based quantum computing. And it turns out that if the Clifford circuit you started with is in a planar geometry, then the graph state simulation problem you'll end up with that's equivalent to it will have a sort of almost planar geometry. And that distinction between planar and almost planar for us is not going to matter, and I'm not going to really go into it. Okay, so for the rest of the talk, I actually just want to focus on this graph state simulation problem. And the main result of our work is that if you give me a graph state simulation problem where the graph is planar, then there's a classical algorithm to solve that with runtime n to the omega over 2. So, so that's our main result. Are there any questions about that?
So where did the D factor go to in this mapping between the original Clifford circuit and the graph state?
Yeah, right. So when you take a Clifford circuit on a planar graph of depth D, you can map it to a graph state simulation problem, which can be coarse-grained to a planar graph, and the coarse graining introduces a cost that depends on D. So like the instance of graph state simulation will not be...
Oh, so the graph itself is not planar, but if you coarse grain it, it becomes planar,
yes,
something like that?
That's right. You should think of it as like every vertex that correspond, like you have a bunch of vertices corresponding to every qubit, and you just treat those, if you just view those as one, then the whole thing is planar, as you might expect.
Okay, okay.
So this is the reason, like this is our main theorem, and this is mostly what we prove. And the reduction to Clifford circuit from Clifford circuit simulation is not that hard, and it's also like nicer to state because we don't have this depth parameter lying around it. Okay. So now I want to tell you about our techniques, and I'm going to spend quite a bit of time on the 2D grid. And so on the 2D grid, we have an algorithm which is actually not quite the same as our more general algorithm, but it tells you many of the things where it has a number of shared features with our more general algorithm. And if all you take away from this section is the 2D grid stuff, I'm happy with that. Okay, so here's our 2D grid. It's root n by root n grid, so the total number of qubits is n. And like, what is the naive classical simulation of this graph state simulation problem on the 2D grid? Well, we start with like all qubits prepared in the 0 state. Remember that to store an n qubit stabilizer state, take like n squared memory. So this is cost of n squared. I'm gonna, by the way, I'm gonna write, like I'm gonna use red to denote vertices corresponding to qubits that we're storing in memory in the classical simulation. So now we're storing all of these qubits in the 0 state in memory. Then we apply the controlled Z gates on all the edges, okay? And each gate, you know, there's only order n gates here. So the cost is order n squared. And then we're gonna measure all the qubits in the given Pauli bases. And as I mentioned before, the cost of that can be, you know, n to the omega. So it you know, using Gosset and Aronson, it would be n cubed, but our algorithm gives n to the omega. And notice that after measurement, I draw the vertices in blue. So qubits that we're done with, they're going to be in blue. Okay.
You need some Hadamards here at some point, no? Otherwise.
Oh, excuse me. Thank you. Yeah. So maybe just replace 0n with plus n.
Yeah.
Maybe this problem persists. I ignored the 1 qubit gates. You're absolutely right. But that can be folded into this first step, the cost n squared. Thank you. Thank you very much for that. Okay, so the total runtime of this naive algorithm is n to the omega, and like if omega is 3, this is n cubed, okay? But this is not going to be the best algorithm, obviously. So now I want to show you a better algorithm, which we'll call the sweeping classical simulation. This algorithm was actually already presented in our 2018 paper with Prof and Koenig. So now we're just going to initialize the qubits in the leftmost 2 columns. So those are the ones in red. And we're going to initialize them in the plus state, okay, not the 0 state. Thank you, Natalma. Then we are going to apply the controlled Z gates in the leftmost 2 columns. How many of those controlled Z gates are there? Well, there's only order root n of them. So the cost of that is going to be n to the omega over 2. We get a square root, you know, we're only doing the square root the number of controlled Z gates. But now, like, look at the qubits on the far left, in the leftmost column. The measurements on those qubits can be performed now before applying the controlled Z gates elsewhere, because those measurements commute with all the remaining operations in the circuit. So we can measure the qubits in the leftmost column. Remember, they're turning blue when they get measured. And that costs n to the omega over 2 because there's only root n of them. And now we can proceed by applying controlled Z gates to the next column, measuring the second column, applying controlled Z gates, measuring, applying controlled Z gates, measuring, and so on, until we get all the way to the end and we've measured everybody. And how, you know, as we sweep across, we have to repeat these steps that I've written here root n time, because we're sweeping across a root n by root n grid. So the total cost here is root n times n to the omega over 2. So it's n to the omega plus 1 over 2. So if omega is 3, remember the naive algorithm was n cubed, this would be n squared. This is a big improvement. Okay, are there questions about that? Okay, but now I'm going to tell you that this is still not the best algorithm. And there's a better ordering of measurements and gates. And so the third algorithm is the recursive classical simulation, and that works in the following way. So the first step is the recursive step. So we imagine that we have an algorithm that does this classical simulation for any grid size, and that the cost of that algorithm is t of n, where t is some function of n that we don't know yet. So in the first step of the algorithm, we look at the 4 subgrids, you know, in these sort of like window pane regions, and we recursively simulate those subgrids, which each have size n over 2. We don't know what the cost of that is yet, but it's going to be t of n over 2, where t is the cost of simulating a grid of size, you know, of a given size. We're going to leave the perimeter vertices, when we do this recursive step, we're going to leave the perimeter vertices unmeasured. So we're going to do the graph state simulation on these little window pane regions, but we're going to leave the boundary unmeasured. Then we're going to initialize all the qubits in the middle, like this sort of window frame part, and perform the remaining controlled Z gate. Notice there's only order root n of them. So the cost of that is n to the omega over 2. And then we can measure all the remaining qubits, and we can either leave the perimeter vertices unmeasured and recurse, or we can measure them all at the final step. And the cost of that is again going to be n to the omega over 2, because like the number of red qubits here is only root n. Okay, so like what is the cost of this algorithm? Is that clear, by the way? So you divide it in 4, you treat the 4 subgrids using recursion, then you connect them together and measure.
I think it's clear.
Okay, so the cost of that is the solution to the following recursion. The t of n is 4 times the t of n over 2 plus order n to the omega over 2. And so now you just need to solve this recursion. And the solution is order n to the omega over 2 up to log factors. So, you know, so again, if omega is 3, like the naive algorithm is n cubed, the sweeping algorithm is n squared, and this recursive algorithm is linear time. Or sorry, not linear time, n to the 3/2. And you know, these improvements are not just theoretical. Like my amazing co-authors implemented these algorithms in a computer simulation, and they didn't use fast matrix multiplication because, as Itai pointed out, that's really only valid for outrageously large n. So you can just set omega to be 3 to understand this plot. So this compares the actual runtime on a computer of these 3 methods for the 2D grid. There are some small differences in the implementation from what I described, but they really are not fundamental in any way. But you can see that the recursive algorithm really does much better as a function. Like the side length here goes, you know, somewhere between 2,500 and 3,000. We're talking about a system of millions of qubits. And, you know, actually they did simulations that were even larger than what is shown on this plot. And the largest one they were able to simulate using this recursive method had 400 million qubits, and that took about 19 hours. So, so the lessons here are that like this kind of divide and conquer method is very powerful, because if you initialize the qubits just before and apply the gates just before they are needed, then you can really vastly reduce the cost of measurement. And you know, you can only store a few small stabilizer states rather than one big one. Like obviously, you know, a 400 million qubit stabilizer state you cannot store in memory. And so, you know, the divide and conquer here is really necessary to be able to simulate such large systems. Okay, so how are we going to apply these lessons to like a general planar graph? Because this is only a special case, right? 2D grid is not everything that we want to consider. And so to handle that more general case and apply these lessons more generally, we need another technical ingredient, which is the idea of a tree decomposition and tree width that I mentioned earlier. So this is going to be a little bit boring, but you know, I'm sorry. It's just, like it might be a little bit dry. Okay, so here's a graph. This example is from Wikipedia. So this is kind of the simplest, interesting example of a tree decomposition. Here's a graph on the left. The vertices are labeled A, B, C, and so on. And on the right-hand side, there's a tree decomposition of that graph. And I'm going to just explain what a tree decomposition is and why this is a tree decomposition. So a tree decomposition of some graph is a tree. So on the right-hand side, you can see that it's a tree. There are no cycles. And at every node of the tree or every vertex of the tree, we call the vertices of the tree a node, just to distinguish them from the vertices of the graph. So for every node of the tree, there's a subset of vertices that we denote B sub I. We call that the bag associated to that node. So like, for example, you know, here, this ABC, the bag is that subset of vertices, A, B, and C. And these bags in the tree have to satisfy 3 properties. What are the properties? First of all, every vertex of the graph is in a bag. So like A is in this bag. And for each one of these vertices, you can check that it's in some bag. What's the second property? Like for any edge of this graph, there is some bag that contains both endpoints of the edge. So for example, if we look at this edge BG, we can find this bag that contains both endpoints. Actually, in this example, there's more than one bag that contains both endpoints, but the property says you only need at least one. Finally, if you look at all of the bags that contain a given vertex, they have to be connected in the tree. So if we look at all the bags that contain vertex B, they're these ones, and they form a connected tree, subtree. So those are the properties of a tree decomposition. And how should you think about this? Well, I can make a tree decomposition of any graph by just making one big node containing all the vertices. Okay, that satisfies all these properties, but it's not interesting, right? The interesting thing is when you can make the bags small, because when you can make the bags small, it really means that your graph is like close to being a tree. And so the parameter that tells you kind of how close to a tree you are is the maximum bag size. And just but for kind of silly reasons, the width of a tree decomposition is defined to be this maximum size -1. So in this example, this is a width 2 tree decomposition because the bags have size 3. Okay. And the tree width of a graph is the minimum width over all possible tree decompositions. So this is a measure of how tree-like the graph is. And why are planar graphs of interest to us, or why are they special in this context? Well, it's been known since the 70s that they admit tree decompositions of width √n, and those can be computed in linear time. Okay, so planar graphs are more like trees than general graphs. Okay. And for our purposes, this is a small thing, but it turns out that the tree decomposition that you can compute in linear time can be, without loss of generality, taken to have a certain sort of nice form, which I'll show in the next slide. So the nice form, the tree is rooted. So here on the right-hand side, there's a root vertex. And there's 3 types of nodes in this tree decomposition. The green nodes introduce new vertices. So you should sort of read it from left to right, okay, moving up the tree. The green nodes introduce new vertices that were not in their children nodes. So for example, like if we look at this BFG node, its child, the bag, is a strict subset of this bag. So the vertex F is introduced here. The leaves are also introduced nodes. They don't have children, but they introduce vertices. These pink nodes are forget nodes. Going from ABC to BC, we have to forget vertex A. So the forget nodes, their bag is strictly contained in their children's bag. The third type of node is a merge node. So here, like BCD, we take the union of the subsets corresponding to their children. Okay, so this is a nice tree decomposition, and for a planar graph, you can compute a nice tree decomposition with, in linear time with all the, with width √n and so on. Okay, so now, given that, given this, and this, I should also mention that this nice tree decomposition that you compute for a planar graph, it somehow comes from this divide and conquer strategy. It uses this notion of a planar separator, and so the structure of this tree decomposition reflects the fact that you can, for planar graphs, divide them into 2, well, okay, maybe I shouldn't get into that, but this is the technical ingredient that we need to describe our general algorithm, which I'm going to describe at some high level now in the last couple of minutes. Okay, so I'm just going to tell you at some high level how this algorithm works, and hopefully this, along with the description of the 2D case, makes it kind of clear what's going on. So we start with our graph, and then in linear time, we can compute this nice tree decomposition, which I just told you about. Now, the next step is kind of maybe the most important step. The next step is that we're going to map the tree decomposition to a Clifford circuit. And there is just a substitution rule for each of the types of nodes. Remember that the nice tree decomposition has 3 types of nodes that are green, pink, and purple here. And there's a gadget which tells you how to replace each one of those nodes with a subcircuit. So let's look at this, these introduced nodes first. So on every introduced node, we just add a qubit corresponding to each vertex in the bag, prepared in the state plus. So here we have ABC. Here we initialize qubits A, B, and C in the plus state. Here we have C, D, and E. Here we initialize C, D, and E in the plus state. Notice, I want to point out here that qubit C appears twice. So we have 2 copies of qubit C in this circuit, okay? Now let's look at the forget nodes, okay? So here qubit, or vertex A is forgotten. And what is the gadget doing here? It's applying all the CZ gates, you know, between vertex A and its neighbors. You know, we're sort of like, the modus operandi here is that we're going to only apply gates at the very last possible moment, okay? So here, qubit A is being forgotten, so we better apply all the CZ gates between it and its neighbors, okay? Likewise here, qubit C is forgotten, so we better apply like the gates that need to be applied to qubit C. Like that doesn't include this gate between A and C because we already applied that one. Okay,
But
what is this?
Forgotten, you mean that it's you trace it out, or what's the operation that you're doing on qubit A?
Oh, yeah, so so right now, nothing. So this circuit prepares a state on qubits that are forgotten here. But I'll talk about that in a second.
Okay.
So these purple gadgets, the merged ones, are a little bit more interesting. Here we actually have to take 2 copies of C and map it to 1 copy of C, right? This vertex C that gets repeated here. So what is this gadget doing? And there's an intermediate measurement here. Well, this is designed so that if the measurement outcome is 0, the gadget implements this isometry that maps 2 zeros to 1 0 and 2 1s to 1 1. And using that fact and the structure of this circuit, it's not hard to show the following key property. So we have all these ancillas that are associated with these merge gadgets, right? These ones in the purple boxes. And if all of those measurements give outcome 0, then it's not hard to show that the state of the remaining qubits, the state prepared by this circuit on all these remaining qubits, is in fact the graph state that we want. Okay, so if you get a 0 outcome for all the purple measurements, you're in good shape, because then you can, you know, just measure all of these guys in the given Pauli bases to do the planar graph state simulation. So what is the, you know, so we've prepared this, remember that we're describing this classical algorithm. So we've described this circuit. The circuit has this nice property. So what's our next step? The next step is to actually classically simulate this circuit left to right and measure all the qubits like A and C and E and so on in the given Pauli bases. Okay, so that this isn't quite right, Because we might not get a 0 outcome for these measurements. But let's just proceed for a moment and just talk about this step. What is the cost of this step for classically simulating the circuit from left to right? Well, I want to point out to you that like, if we just consider like simulating like these first couple of nodes here, you know, we can simulate this part and this part separately. So instead of having 6 qubits here, we have 2 sets of 3 qubits that are unentangled. And then, you know, when we, each time we moved through this circuit, like, you know, we can measure this qubit A in its given Pauli basis before moving over here, right? So at every step, the number of qubits we have to hold is at most like the sum of the bag sizes. Like we have a bunch of states, 1 for every bag, and we're performing measurements on each of those states. So the cost of that is like the cost of doing Clifford simulation on a bunch of, you know, a bunch of quantum states of size equal to the bags. So we get a runtime which is like the sum of the bag sizes to the omega. And well, this might seem like magic, but the structure of the tree decomposition that is derived from, you know, that you get from these planar graphs, it has the feature that if you can upper bound this quantity, the sum of the bag sizes to the omega as n to the omega over 2. So that's good because this is the runtime we want. But
sorry,
as I said,
but isn't the size of BI is n over 2?
No. So each bag, remember the tree width is root n. So each bag has size at most root n.
Oh, okay.
But in fact, like that bound is not enough to.
So sorry, so root n, yeah. So just BI to the power of omega is n to the power of omega over 2, right?
That's right.
But then you have a bunch of them. So how many bags do you have there?
Right. So because it has this kind of this structure where it's sort of you're dividing the qubits every time you do this merge. Like this tree decomposition has a nice structure where the bags get smaller as you move down the tree. Like they get sort of exponentially smaller at each level. So
okay. No, because in the picture it looks like as if they are the same size.
Yeah, but this is not actually derived from a planar graph. You see, for planar graphs, you have this nice structure where the bags get smaller.
I see.
Yeah.
Okay.
Okay. So this, as I said, this isn't quite what we want, because if you do this, you get the right runtime, but these purple qubits that you measured might not all be 0, and then you might just, So as I said, if we get lucky, we're done, because if the measurements in purple give outcome 0, the output is correct. And one thing that I will not talk about, but which is true and kind of, actually turns out to be, in this example, not so much work, but in other examples we consider to be more work, that if you get a wrong outcome, so if the measurements actually give outcomes that are not all 0, then you can in linear time correct it into a good outcome. And the correction involves finding a stabilizer of the state of a certain form. And again, you can do that using the tree decomposition. Okay. So
I mean, David, so the purple bags are actually, in this example, they're like 4 qubits, right? Bags of 4 qubits in some sense. I mean, you have to see 4 qubits. I mean, does this somehow change? That does not affect the scaling of this?
Sorry.
Like in it, for this purple, when you want to simulate the outcome of the purple circuit, the purple bag, you have to kind of simulate the four qubit state, or
so there's only one measurement in each of those bags, and that's what I'm talking about here when I say that they have to give outcome 0, just this one qubit measurement, each of those. But this cost of simulating these 4 qubits is included in this sum of the bag sizes to the omega, because one of those bags here would be 4, right, or 2.
Oh, okay, I see. Okay.
Okay. So there's this key thing that I didn't really explain here, and that I'm not going to explain, that these wrong outcomes can be corrected by finding a stabilizer of the state prepared by the circuit with a certain property. And again, we use the tree decomposition to find that stabilizer in linear time. Okay, so now that's kind of the end of how I'm going to describe the algorithm in this talk. And now I just want to, in the last slide, mention some extensions and generalizations that appear in our paper. So, our algorithm, what's special about planar graphs for us is that they have these nice tree decompositions from planar separators that can be computed quickly. But if you have another graph with where you can compute a tree decomposition, so if you give me a tree decomposition of a different graph, and the tree decomposition has width t, then you can still use our algorithm, and the runtime will depend on n and t in the following way. So if you plug in a planar graph here and t is root n, this scaling is not as good as what we achieve, because as I said before, in the previous slide, we actually use the structure of the tree decomposition, not just its width. We actually consider a more general version of graph state simulation in our paper, where you can post-select the outcomes of certain measurements. And that turns out to be somewhat more powerful, and it allows you to generalize from Clifford circuits to so-called Clifford tensor networks, which I don't really have time to describe here. Okay, and that's it. So happy to take questions if there's time.
Thank you very much.
Okay, questions. Itai, you had a question?
I was just wondering, it's very nice, by the way, but if I go back to the square grid example that you had without all these three compositions. So,
oh, what happened here? Sorry, did my thing disappear?
I think it's on your side.
Is this better now?
We see things. Yeah, we see the last slide.
Okay, so I'll go back to the 2D case and without the tree decomposition. Yeah.
I just want to it's a silly question. I just want to understand. So what exactly happens if you don't have a Clifford circuit? If you have a regular circuit and you use and you try to to use your method in some sense on a one-way computation scheme.
Yeah.
There also you map it to this graph state, right? And you do single qubit measurements, etc. Can you use this kind of trick of yours to speed up things, or?
Yeah, I mean, that's an interesting question. I mean, so like this sweeping algorithm actually, you know, like Isaac Kim, for example, has proposed using this for simulations of universal circuits in 2 dimensions, right? That you know, he calls it holographic algorithms, where you have a 2D circuit you want to simulate, but you do it sweeping in using a 1-dimensional quantum computer. And you know, obviously, there's an improvement in terms of the amount of memory that you need for that, because instead of simulating it, you know, if you have like, instead of a 2D quantum computer, you can have a 1D quantum computer. But now if you go to the recursive case, is there actually an improvement for like universal circuits? I don't know, because you still need to have like a linear number of qubits in your quantum computer, right? Mm-hmm. So I think that the sort of divide and conquer strategy, it gets washed out, I think, when you have exponential cost for each operation. Like, I'm not sure that, I don't see, I guess the answer to your question is I think it's an intriguing question, but I don't see how to benefit from this divide and conquer scheme for, you know, on a quantum computer. Does that answer your question?
I guess so, but if I even go back to the first idea that you had, even just one column by.
Yeah.
So if it's just a regular, not a Clifford thing. Yeah. Then the problem would be what? That it's too entangled. I mean, if you want to simulate the results of a single measurement.
Oh, are we talking about classical simulation or like using a quantum computer?
Classical simulations.
Okay, so certainly you can classically simulate a universal circuit in this way. You know, I think that this is not so far off from the tensor network contraction ideas, mm-hmm. right? In fact, like, you know, if you look at like Aronson, yeah, I mean, so I think it's roughly the same actually idea as the tensor network contraction, because you're
I just want to understand, where does the exponentiality blows in your face here? Because this,
well, you still need to store root n qubits, right? So like everything in red is being stored in the classical computer's memory.
Yeah, but it seems like as if there is almost no entanglement there. No, I mean, or it's just an artifact of the picture. I don't know, but because the blue guys have been in some sense measured, so they are in some sense decoupled from the red guys. So I just.
Yeah, that's right. No, I think, I mean, you know, it's true that as you know, I mean, the entanglement in 2-dimensional circuits is not the same as an entanglement in a general state. And I, you know, I think, yeah, it is true that you can simulate it in this way, and the cost will be exponential in root n, right?
I had a related question. Maybe also we'll go back to Itai's question. Mm-hmm. But I mean, suppose I consider a different problem, a slightly different problem, where I wanted to do this graph state simulation, but I wanted to update my measurement basis depending on measurement outcomes during the. Would this?
Yeah.
And I wanted to classically simulate that.
But we're still talking about Pauli measurement basis, so it's still Clifford. Okay.
Right. Mm-hmm. But I would like to update them somehow based on.
Well, then you need to choose an ordering of the measurements, right?
Right.
And so that freedom to choose the ordering, you know, we are using that freedom to choose the ordering in our algorithm. But if you want to beforehand choose an ordering, then, you know, then you probably can't use our algorithm directly, because our, you know, when we run this algorithm, like for example, in this recursive case, we choose to measure all these blue vertices first. But if you told me that those have to be measured last, then I wouldn't know what to do.
Right. When you could still do the kind of suboptimal thing you showed before. Yes. Suppose I wanted to think about this kind of as a measurement-based quantum computer, but in a Pauli basis, which is not universal somehow. I could still do the left to right thing you showed before,
Well, it depends though. I mean, it depends whether or not your ordering requires me to do it in a different way, right? I mean, because if you tell me that the things on the right have to be measured, like have to be measured first, and then things on the left depend on
Right.
them.
No, but think about like a measurement-based scheme where I kind of run it.
Oh,
left to
sure.
right. Yeah.
Yeah. So usually those schemes, the time dimension, yeah, would be going left to right.
For example, then I could, yeah, you could still kind of, it's not, you can just, you know, you don't need all the cluster state to be alive at the same time.
Right.
Yeah. So, I mean, right. So somehow the question of, I think Itai's question of doing a universal quantum computation also somehow requires doing some feedback and, you know, forcing some somehow sequence of measurements.
No, I understand now that it just creates too much entanglement every column like that, and I mean, unlike Clifford measurements that you can simulate efficiently here, I mean, if your measurements are not Pauli measurements, then you would just need to store all this exponential state in your memory, probably, right?
I think you still don't need to store more than what's drawn in red here. But that thing in red still has size root n. So
yeah,
storing that will cost exponential in root n.
Right.
Yeah. Okay. And you can probably use the same thing. I mean, do a slightly simpler analysis using this image of a bubble swallowing this graph if it is not a square. I mean, instead of using the tree mechanism and the tree width, I mean, if it was just not a grid graph, not a square grid, but a different type of grid, then you can still imagine some sort of a bubble swallows it, and then on the intersection between the bubble and the grid, do the same trick that you did here. I mean, just measure.
Yeah, I'm not sure. I mean, so I'm not sure. I mean, so in fact, we were basically unable to generalize this recursive algorithm, you know, which is why we went to the tree decomposition based thing. The planar separator theorem, like, it gives you these separators, but like the main difference between this 2D algorithm and the more general algorithm is the replication of qubits. When you have a tree decomposition, you replicate qubits and then merge them later. And for us, we couldn't find a way to get around that, but we don't know that it's necessary.
Okay, I see.
Okay. Other questions?
Just to be sure, the place where omega keeps popping up is just because it's the cost into the omega is the cost of simulating a Clifford circuit with n qubits?
Yeah, if you want to measure all the qubits at the end, and if the circuit, in fact, you know, if you have a very high depth circuit, it can cost more than that. But like if, for example, your circuit contains only a layer, like if it only contains CZ gates and single qubit gates, then yes.
And that comes from like some matrix from, I mean.
Yeah, we have an appendix to our paper. It's not so simple, but it is kind of like, I think, you know, if you are a person that is happy with the kind of techniques that are used to get matrix multiplication time speedups in other places, you know, you might look at it and say that it's straightforward, but I look at it.
It's not just a reduction
like
to
magical.
matrix multiplication.
It's not completely straightforward. No, it's like a fairly long appendix.
Can you say something about this? How this post selection allows you to do tensor network construction? Yeah,
well, so yeah, how does that work? So first of all, what is a Clifford tensor network? Right? I mean, so a Clifford tensor network, you know, a tensor is a matrix with, you know, and you represent it, like, for example, in this picture, you know, you have a bunch of legs, which are the indices of the matrix, of the array. And we would say that a tensor, so in this picture, like a tensor is a Clifford tensor if you view it as a vector, so view it as a vector where each of these indices, so each of the indices will have rank 2, will take 2 values, so like I1, I2, J1, J2, J3, they'll all take values 0 or 1. And so we can view this has 5 legs, so we can view it as a vector of length 32. Okay. And if you view it in that way and it's a stabilizer state or proportional to a stabilizer state, then we would call it a Clifford tensor. There's equivalent definitions, but that, you know, and then when you have a Clifford tensor network, you know, that's just, you take a bunch of these elementary Clifford tensors of constant, each one of constant size, and you take a bunch of them and connect them together.
Yeah.
And, you know, post-selection lets you do kind of, like, what is the difference between a circuit and a tensor network? I mean, you know, one difference is that you can do like isometries or like non-unitary operations. And of course, post-selection lets you do that. But another difference is that things are not connected in this kind of like linear order, that like you don't have like a sort of ordering the same way that you have for a circuit. So sorry, I mean, I guess I'm not sure that I'm completely answering your question. I'm kind of like going around the question, but you know, in our paper we have like a reduction which shows you how to do this using this thing called a Hadamard gadget, which is similar to this measurement-based quantum computing thing. But I think the intuition is that post-selection lets you do non-unitary operations, and that's one of the major differences between.
By post-selection, you mean post-selection kind of in the classical simulation?
Yeah. So like for example, like in a Clifford circuit setting, let's say you wanted to measure all the output qubits and sample from the conditional distribution, conditioned on the first 5 of them being 0. So our algorithm actually lets you do that in the same amount of time, n to the omega over 2.
Does that mean that you can use, if you have a general tensor network and a large fraction of it is Clifford tensor networks, and you can have some edge, some advantage in contracting it in some sense using your method?
Well, our algorithm is for sampling. So the question of whether or not you can keep track of the global phase is relevant. Yeah, so you know, your question touches upon whether or not, or it's relevant to the question of whether or not this can be incorporated into like these sort of stabilizer rank based simulation algorithms where you sort of take a universal circuit and write it, the unitary, say, as approximated as a sum of Clifford circuits, and then try to sort of use Gauss-McNeil to simulate it. And those algorithms actually require a sort of version of Clifford simulation that keeps track of global phases. And we don't present that in our paper. And we're interested in whether or not that's something we can do.
Okay, thanks.
All right, other questions? Okay, so David, thanks a lot for a really wonderful and clear talk.
Thank you.
Thank you. Thank you.
Pleasure hosting you. Hope to see you again soon.
Yes, thank you very much. It's really nice to meet everyone, and you know, it's nice in the pandemic to be able to see people across the world. Thank you again.
And have a good rest of your day.
Okay, you too. Bye now.
Bye.
All right, bye-bye.